Welcome back to physics. This lesson is all about Newton's second law. The last one was Newton's first law, and Newton's second law is related to Newton's first law. So we're looking at what Newton's second law says about force and acceleration, and what is this thing called inertial mass. And then we'll be looking at using Newton's law in context. Before we get into it completely, I want you to pause the video for 5 minutes and have a go at the quiz. Are you ready for some answers? Number 1, distance equals speed times time, or you could have said speed equals distance divided by time. Number 2, acceleration equals change in speed divided by time, or you could have written A equals V minus U over T. Number 3, work done equals force times distance. Number 5, force equals spring constant times extension. Number 5, force equals mass times acceleration. And number 6, weight equals mass times gravitational field strength. Those equations are all ones that you need to memorize. You will not be given them in the exam. Number 7, to find the resultant force, you add up all the forces in one direction and then you take away all the forces in the opposite direction. Number 8, terminal velocity means the constant velocity that you reach once all the forces are balanced, so the resultant force is 0. An example could be a car reaching its top speed when you're accelerated as much as you can, or it could be the constant speed that a skydiver falls at once the air resistance is equal to their weight. Number 9, air resistance increases with surface area and with speed. Number 10, velocity has a direction, speed doesn't. Velocity is a vector, speed is a scalar. Or you could have said velocity is just speed, but with a direction. All right, now we've reminded ourselves of things we hopefully already know. Let's move on. This is the wordy version of Newton's second law of motion. The acceleration of an object is directly proportional to the resultant force acting on it, and that little symbol there between the A and the F is the symbol for direct proportion, and inversely proportional to its mass. So A is proportional to 1 over m. That is really wordy, and as I've probably said before, us physicists are kind of lazy when it comes to words. We really like symbols and formulas. So if you're ever asked to write down Newton's second law of motion, you can write that. Because if the acceleration is proportional to the force, and the acceleration is also proportional to 1 over the mass, then the acceleration must be equal to the force divided by the mass, if you put those together. And if you rearrange that, you get F equals ma. All right, we're going to do these 2 examples. Now, if you want to pause the video and do them yourself before I do it, that's absolutely fine. If not, you can just keep watching. If you haven't noticed already, there is actually a sheet, the Activity 1 worksheet that goes along with this video, has all the questions that I'm going to talk through on screen on it. So if you wanted to pause the video and go print that out, and then you can do them along with me, rather than having to peer at a screen. Okay, so a car with a mass of 900 kilograms accelerates from rest with an initial acceleration of 2.5 meters per second squared. Calculate the resultant force required to produce this acceleration. First thing, underline your data and write yourself a list, and then put a box around the thing that you need to work out. Check the units. We've got kilograms, we've got meters per second, so I don't need to convert anything. Then you write down the equation, you substitute what you know, and you work it out. Same idea with the next one. However, there's a bit of a catch. Car with mass 1,250 kilograms, that's straightforward, has an engine that provides a driving force of 5,200 newtons and we've got a drag force of 5,100 newtons. Find its acceleration. So they've given us two forces, so which one do we use? The answer is kind of both, because we've got the driving force forwards, that's the thrust of 5,200 newtons, and we've got the drag backwards of 5,100 newtons. Remember last lesson we were doing force diagrams? So the resultant force is only 100 newtons, and it's to the right. So we're working out the acceleration. Now we know the mass, we know the resultant force. Write down the equation, substitute in the numbers that we know, and work out the answer. And remember to give the units, meters per second squared. There's quite often a mark for knowing that unit, and that will come up when we do the past paper questions a bit later on. Okay, pause the video and give yourself a couple of minutes each, so 10 to 12 minutes, and do these questions. Remember, you can go to the Activity 1 worksheet, print it out, and you can do it on that page if you want. Ready for some answers? There you go. Pause the video and mark your work. Let's do a little reminder. Can you remember what Newton's first law was? Have a think for a minute, see if you can remember from the last video. Well, Newton's first law told us that if the resultant force is zero, the velocity won't change. You need a resultant force to change a velocity. So Newton's first law and Newton's second law are connected, because if you need a force to change the velocity, that's Newton's first law, and Newton's second law is telling you how the velocity will change. So Newton's second law is kind of building on top of Newton's first law. That brings us to the idea of inertia. Inertia is just the tendency of an object to continue at the same speed in a straight line. So Newton's first law exists because of this thing called inertia. I think of inertia as being like the kind of laziness of the universe. Everything just wants to keep doing what it's doing without change, and that is inertia. So we have this thing called inertial mass, and that's the proper term for mass. It's a measure of how difficult it is to change the velocity of something, and inertial mass is defined as resultant force divided by acceleration, or some places you see it described as it's the ratio of resultant force to acceleration. And ratio in this context just means you divide. To get an idea of what it is, have a look at the picture there. We've got a bowling ball and a tennis ball. Let's say those were both coming towards you at 5 meters per second. So they're both going at the same velocity towards you. Which one of them is going to need a greater force to stop it? So which one do you have to apply a greater force to when you catch it? It's going to be the bowling ball. It's got a much larger inertial mass, so you have to apply a much larger force to change its velocity. All right, let's review what we know so far. Pause the video for about 5 minutes and answer these questions. Are you ready to mark your work? There's the mark scheme. So pause the video again and mark your work. All right, are you ready to try applying what you know in context? Pause the video and answer these. You'll probably need about 10 to 12 minutes. Are you ready to mark your work? There's the mark scheme. So pause the video and mark what you've done. All right, let's move on. Here's an exam question. Now you might recognise this. This is part B of a question that we started in the last lesson. If you want to pause the video and have a crack at the questions yourself, that's great. Go ahead, do that. If you just want me to talk you through these ones, again, that's absolutely fine. Keep listening. So here we've got our aircraft moving along the runway. It has a takeoff mass of 320,000 kilograms. Each of the 4 engines can produce a maximum force of 240 kilonewtons. Calculate the maximum acceleration of the aircraft. Show clearly how you work out your answer and give the unit. Okay, let's see how we tackle that. First thing, write down the data. There's the mass, nice and straightforward. Now it tells us we've got 4 engines and each one produces a maximum force of 240 kilonewtons. So we've got a couple of things to do there. For a start, we've got to multiply the force by 4 because we've got 4 engines. Second thing, that's kilonewtons. So we've got to do 4 times 240,000 newtons to get the force. And if you did that to get 960,000 newtons, well done, you got the first mark. Next thing we need to do, highlight what we need to calculate. And there it says give the unit. So if I put the unit in there, I've now got 2 marks out of the 3 that this question is giving you. So we need to write down the equation, substitute what we know, and work out the answer. This is an old spec exam question back when they used to give you an equation sheet. In a new exam paper, if they had the same question, it would probably be worth 4 marks instead of 3, because they'd give you a mark for knowing the equation and then a mark for substituting and getting the answer. Here's another exam question. Again, if you'd like to pause it and have a go, feel free to do that. If you'd rather I talk you through it, again, that's absolutely fine. So we've got an old question here about the space shuttle. We've got a table of data. We might not need all of that data. That's one of the reasons this is a higher tier question, is you've got a pile of data there about the orbiter and you don't need some of it. After touchdown, the orbiter decelerates uniformly, coming to a halt in 50 seconds. There we go. You can do it in words or you can do it in symbols. They're both fine. Calculate the deceleration of the orbiter, show clearly how you work out your answer, and give the unit. All right, let's have a look at what we can do. Well, we've got it decelerating uniformly, coming to a halt in 50 seconds. So we know the final speed was 0 because it's coming to a halt, and we know the time was 50 seconds. We have to calculate the deceleration, that's A, and it looks like we've got some missing information. We need the initial speed. Now it says give the unit, so I've put that in already. As soon as it says give the unit, honestly, go to the end of the question, write down what the unit's going to be, make sure you don't forget that mark. If you look at the question, it says after touchdown. So we're talking about what happens after the orbiter has landed. So to pick that out of the data, we need the landing speed of 100 meters per second. So the initial speed was 100 meters per second. We don't want the orbital speed because that's the speed before it lands. So we write down our data. We've got the equation already in the question before. Substitute the data in, work it out. And with this one, if you missed off the negative sign, that's okay. they don't mind if you've missed that off. Part C, give the equation that links acceleration, force and mass. There you go. Force equals mass times acceleration. That's our Newton's second law equation. Or you could just write F equals ma if you like. Part 2, calculate in newtons the force needed to bring the orbiter to a halt. Show clearly how you work out your answer. So let's look at our data. We're calculating the force. We've got the acceleration because we've just worked that out. And we need the mass. There it is. Mass 78,000 kilograms. So let's add that to our list. F equals m times a. Substitute in the data. I've dropped the negative sign from the acceleration because it's not asking me whether the force is forwards or backwards. It would be backwards, it would be negative. So if you've left it in, that's fine. I've dropped it because in this question, it's not needed. It's only 1 mark. If it was 2 marks, I would probably leave it in. All right, pause the video and do the Activity 2 exam questions worksheet. Give yourself about 20 minutes. The first question is foundation, so if you look at the first question and think, that's way too easy for me, you can miss it out if you want and go straight on to question 2. If you'd like to do question 1 as a kind of warm up to the standard demand questions, that's absolutely fine. You can do that. These exam questions are mostly Newton's second law. It's very rare to find an exam question that is only on one thing. So you'll find other parts of physics are creeping into these. For example, the first question there involves an understanding of density, even though you don't have to work out anything to do with density, and weight. Some of the other questions might involve Newton's first law or Newton's third law. So let's get on with these. Okay. First one, question 1. This is a foundation level question, and I'll point out why in a minute or two. We've got a diagram showing 4 blocks of different materials floating on water. The 4 blocks are the same volume. On the diagram, circle the block that has the smallest weight. It's fairly simple. It's going to be C, because if it's got the smallest weight, then it's going to float the highest. It's not going to displace as much water as the heavier blocks. Figure 2 shows a lifebuoy next to a deep swimming pool. The lifebuoy has a mass of 2.5 kilograms. It gives us the gravitational field strength. To calculate the weight, and you can tell it's a foundation question because they give you the equation. On a higher tier question, they will not give you the equation ever. Alright, so let's see. We've got a mass of 2.5 kilograms, so actually it looks like they've kind of given you the list of data already. They made it easy for you. Mass equals 2.5 kilograms. I'm going to do it anyway because it's a good practice. Gravitational field strength. Use the equation. Normally at this stage I would say write down the equation and then substitute, but they've given us the equation, so I can just substitute straight away. And that gives me an answer of 24.5. They've given us the unit, so I just need to write my answer down in the answer scheme. C. When thrown into the water, the lifebuoy floats. The 2 forces acting are the weight of the lifebuoy downwards and the thrust upwards. If this hadn't been a foundation paper, you'd probably have been asked a more detailed question, maybe to draw the force diagram or to name the forces. But this one gives you some of the information. Okay, so it's floating, therefore the forces must be balanced, so the size of the forces must be the same. Right, when it gets to D, that's a more typical kind of question. On the second half of a foundation paper or the first half of a higher paper, they'll give you a question like D where they ask you what the equation is first. Once you get to the back end of a higher tier paper, they don't give you that hint. They just go straight into the question. So write down the equation that links acceleration, mass and resultant force. You can use the words if you want. I'm not going to. I'm going to say F equals ma. So it's okay to use symbols as long as you use the standard symbols. You know, F must be a capital F for force. M and A must be a lowercase for mass and acceleration. E. A rope is used to pull the lifebuoy to the side of the swimming pool. A resultant force of 4 newtons acts on the lifebuoy. The mass of the lifebuoy is 2.5 kilograms. Calculate the acceleration of the lifebuoy. Okay, so we've got the equation up here. I'm going to write it again. I don't really need to, but I prefer having everything all in one place. So I'm going to substitute in my data. And at this stage I've already got at least one of the marks. So I've got to do that. There we go. So the marks here, there's 3 marks for it. There's 1 mark for the equation there. These 3 marks, there's a mark for substituting, a mark for rearranging, and a mark for getting the answer. Question 2 is a standard demand question. So you might find that in the second half of a foundation paper or the first half of a higher paper. So we have a boat pulling a water skier. And here we've got a diagram, we've got an arrow pointing that way. The arrow represents the force on the water produced by the engine propeller. This force causes the boat to move. Explain why. This is actually a Newton's third law question, which we've not done yet. Newton's third law is the one that says for every action force there is an equal and opposite reaction force. So let's look at this one. We've got the arrow represents the force on the water produced by the engine propeller. So we need to turn that round and say there is an equal and, you guessed it, opposite force. Now this question wording, on the water produced by the engine propeller, so turn it round, on the propeller produced by the water. And that is using Newton's third law. For every action force, there's an equal and opposite reaction force. So if you're standing on the floor, there's a force from your weight on the floor. There's an equal and opposite reaction force by the floor on your feet to hold you up. Otherwise you go crashing through the floor. Right. B should look a little bit more familiar. The first video lesson would have given you the information to be able to answer part B. The boat accelerates at a constant rate in a straight line. This causes the velocity of the water skier to increase from 4 meters per second to 16 meters per second in 8 seconds. So there we've got the initial speed and the final speed. Remember, V stands for velocity, U comes before V, so U is the velocity before. That's the initial velocity. Time of 8 seconds. So this one doesn't give us the equation. We need to know that. It's one we need to memorise. So A equals V minus U over T. Or if you don't want to do that, if you say acceleration is change in speed divided by time, you can look at U and V and you can say, well, the change in speed must have been 12. And it kind of skips out a step a little bit. So if I put that, so let's see, I'm calculating the acceleration, so it's A that I don't know. So I can say A equals 16 take away 4 divided by 8, which is 12 divided by 8, which is 1.5, and there's nothing here. There's no unit given. So I need to give that. There we go, and give the unit. That was me not reading the question. Normally, I would do that bit first as soon as I see it. Very easy to miss. The water skier has a mass of 68 kilograms. So let's write that in a little list. We've just worked out the acceleration. Now, for this question, if you got that value wrong, but then you used it here, whatever you worked out, you can still get these marks. So say you worked that out and you did, it was just 16 divided by 8 and got 2. If you used 2 here, but did it the same way as I'm showing you, you can still have both of those marks, because you've already lost the mark here. Right, calculate the resultant force acting on the water skier while accelerating. So I need to write down my equation. Again, this is one that you need to have memorised. F equals ma, or force equals mass times acceleration. Calculating the force, so substitute in what I've got, which is 102 newtons. And they've given me the units there, so I don't need to worry about that. Draw a ring around the correct answer to complete the sentence. The force from the boat pulling the water skier forwards will be something than the answer to this one. I mean, it's going to be greater than. That's the resultant force. Now, if I look at a diagram here, if I draw a diagram, we've got the forwards force from the boat. So let's call that the thrust force. And that is 100, no it isn't. That's what we don't know. We've got some friction, or some drag, and the resultant is 102 newtons. So the thrust, take away the friction, is 102. So the thrust must be bigger than 102 newtons, so that's greater than. So we need to say down here, we have to overcome resistance, or we have to overcome drag. Question 3. When a car is driven efficiently, the engine gives a constant forward pull on the car as the car accelerates to its maximum speed. During this time, the frictional forces and air resistance oppose the forward motion of the car. Oh, this is reminding me of Newton's first law from the previous lesson. The sketch graphs below show how the car's speed increases when only the driver is in the car and when the driver has a passenger in the car. Okay. How does the acceleration of the car change with time? Well, let's have a look at these graphs. So down at the bottom here, we've got quite a steep line. Up here, we've got a much shallower line. So the gradient is decreasing. So if the gradient is decreasing, well, the gradient is the acceleration. So how does the acceleration of the car change with time? Decreases. What conclusion can be made about the resultant net forward force on the car as its speed increases? Well, as its speed increases, the acceleration decreases. Resultant force is proportional to acceleration, so the resultant forward force must also be decreasing. And the last bit there, I should say 3. On the graph, Draw a line to show how you'd expect the car's speed to vary if it carried 3 passengers. Alright, well there's driver alone, driver and passenger. So continue the trend. If you had a driver and 3 passengers, it's going to be much lower. As far as the mark scheme is concerned, they're not looking for how far down it is. As long as your line is lower everywhere than this one, you'll get the mark. Right, part B. The manufacturer of a family car gave the following information. Mass of car 950 kilograms. Okay, let's just do a little data list. The car will accelerate from 0 to 33 meters per second in 11 seconds. We've got U, we've got V, and we've got T. Calculate the acceleration during the 11 seconds. Okay, so we're doing change in speed divided by time. (33) take away 0 divided by 11, which is 3, and the units aren't there, so I'm going to have to write them in. Usually they do tell you and give the unit as a little reminder. For this one they didn't. I think it might be an older question. Calculate the force needed to produce this acceleration. So we need our equation. We've got the mass. We've just worked out the acceleration. And we're calculating the force. So 950 times 3 is 2,850 newtons. The manufacturer of the car claims a top speed of 110 miles per hour. Explain why there must be a top speed for any car. So we've got Newton's first law creeping in again here. So we need to say air resistance increases with speed. Until air resistance is equal and opposite to the engine thrust. If that had been a 3-mark question, I would have added resultant force equals 0, therefore no acceleration. Question 4. This is a higher tier question because you have to find the data in the table. So typical data for an oil tanker. So you'll always get these questions in context, but honestly, mostly what I'm looking for is where is the data that I need to work out whatever they've asked me to work it out. Write down the equation which links acceleration, force and mass. Force equals mass times acceleration. You can write it in words if you prefer. The exam board doesn't mind. Calculate the deceleration of the oil tanker. Show clearly how you work out your answer. And a quick check of the answer line. They've given us the unit, so I don't have to worry about that. Okay, let's have a look at the data we've been given. We've got the mass. We've got the cruising speed. There's no speed in that formula. We've got the deceleration force. I've got the stopping distance. We don't need it. It's interesting though that for the stopping distance for an oil tanker, is 10,000 metres, 10 kilometres. Can you imagine having to put the brakes on when you're still 10 kilometres away from your destination? But that's in the next lesson. Okay, so we've got F, we've got M, we're working out A. So F equals ma is written up there. I'm going to write it down here as well because I'm like that, to be honest. Force was 392,000. Mass was 56 million. So I've got to do 392,000 divided by 56 million. And that comes out to be 0.007.